Welcome to the third lecture of the course on process control, analysis, design and assessment. In the first two lectures, I introduced the general notion of feedback control. I gave you a real life example of control, how we use control. While doing that, we talked about several concepts, one of them being modeling, a model for the process and so on. So, in this third introductory lecture, I am going to talk about modeling more generally to give you an idea of what we mean by model, what is a dynamic model and so on. And later, once these introductory set of lectures are over, we will look into the mathematics behind how modeling is done in lot more detail. So, if you take a processing unit, it could be a chemical process for example, what you have are raw materials coming in and then you have products, and then you can think of this box itself as the processing unit, a plant, which basically works at converting these raw materials to products. So, whenever we talk about models for a process, basically what we are saying is we are going to mathematically capture how this transformation occurs in the process. So, when we talk about mathematically capturing something occurring, basically what it means is that we are going to write equations that relate the outputs to the inputs to the process, and these equations can be of several types. The most common type of equation that you would have seen is the algebraic equation. These equations could be differential equations, ordinary differential equations, or in more complicated cases it could be partial differential equations and so on. So, in general, for any complicated process, if we mathematically model the process, we are ultimately going to end up with equations. That is the first idea that you want to remember. Now, how do I come up with these equations? There is a very structured way of thinking about how will I come up with these equations, which is what we are going to see as we go forward in this course. Now, this is for a complicated process. In this lecture, we will start with a very simple example to give you some nomenclature and to give you some idea of what we mean by a dynamic model and a simple model. Here I am not going to talk about the whole process of modeling, which I will do later, but simply appealing to intuition, we can write a model for this, so that we can understand how we define these variables and how we use these variables in a model. So, if you take a tank for an example, a very simple example, I have flow, let us say, into the tank, and I have flow out of the tank, and there is a height of the tank. So, if I want to model this process, then basically what we are saying is we are going to write equations that relate these variables to one another. Now, there is also an area for the tank which is given in meter square. Let us assume that this tank is a rectangular tank or a cylindrical tank with cross sectional area A. Now, there are several variables here. So, we have Fi, F0, H, A and so on. So, I am going to use or define some nomenclature. A process variable that indicates the current process condition. In this case, I would say Fi is some process variable, it is a very specific process variable which we will come to later. F0 is a process related variable, H height is a process related variable. However, we would call this A as a design parameter. The A value, the area of this tank is fixed once we have the tank in place, that is once it has been designed. So, it is not changing while the process is operating. So, we might think of variables as being the process variables or design variables such as A. Now, these process variables could be further categorized as input variables, output variables or measurement variables, or state variables. So, I am going to explain each one of these in this lecture. State variable is an important concept, and it is also slightly difficult concept in the sense that sometimes it feels that we call some variables as state variables arbitrarily. Sometimes it feels that we could have equivalent sets of variables being called a state variable and so on. So, you need some experience to understand this fully, but in very simple terms, a state variable is one that is very critical to the process or which is inherent to the process, or knowing the value of which I can characterize the process very well. So, that is a very simple layman definition of a state variable. So, if you look at a process like this, then the set of variables that I am going to call as state variables are the ones which are the minimum set of variables which completely describe the state of the system. So, let us see what this means in this simple example. So, if I draw this tank as my system, then you notice that this flow F naught is coming outside the system. So, in some sense it characterizes the system. Now, this H is an inherent part of the system because it is height of the tank. However, if you look at this Fi is a flow into the system. So, if I draw my battery limits for this process as this block, then Fi feeds into the block, or it is an input variable, or it is exogenous to the system, which is outside the system. Something else is changing this, and this comes into this tank as this picture is drawn. So, now if you look at this, then I would call this H as a state variable, because once I know the value of H, then I can completely characterize the system. What I mean by this is, if I know H at any time, then as long as I know this exogenous variable value at all times, then I can completely characterize the system in terms of how much water is there in the tank and what will be the output flow rate, because this output flow rate will depend on the height. So, once I know height and I know Fi, which is exogenous to the system, then I could, for example, write a model and integrate it, and I will know the value of height at all times, and I will also know the value of F naught at all times. So, that is the reason why we call this a state variable. Now, in this example there is only one state variable, but in other examples there could be more than one state variable, and in some examples there could be hundreds of state variables and so on. State variable definitions are not unique. If I have 3 state variables, I can come up with 3 equivalent state variables and so on. So, that is something that you should remember. And one simple way of defining a state variable for the type of models that we are going to look at are, in general, these are the variables for which we write a derivative, and I will explain this in more detail later. So, as far as this example is concerned, I have the state variable H, I have the input variable Fi, and I might say this F naught is the output variable, A is a design parameter. So, which is what we have written here. Now, the process dynamics refers to the unsteady state or transient behavior of the process, where the state variables keep changing over time. So, if you change the input, or if you suddenly change the state variables from where they are, these two changes are going to have an effect on the state variables and how they change over time, and capturing this change in the state variables over time is what is called a dynamic model. It basically captures the unsteady state or transient behavior of the process. And you might ask, why do I need to worry about dynamic models? In real processes, there are always changes that are occurring. The changes could be due to the environment, they could be due to process upsets, they could be induced by us. We want to change a set point, remember the servo control that I talked about before, or there might be a plant which you are starting up. So, there will be dynamic changes when you have startups, and there are times when you want to shut down the plant for maintenance and so on. So, you will have transients there. You could have disturbances. You could actually move the plant from one state to another because you are producing, let us say, polymer of type A, and then you want to change the process to produce polymer of type B and so on. So, these are all the reasons why dynamics is introduced into the process. So, mathematically we want to represent these changes, and mathematically we want to relate the variables in a process. So, the typical type of equation that one writes are differential equations, and once you have a set of differential equations, then if you have unsteady behavior, at least one of the time derivatives will be non-zero. So, once the time derivative is non-zero, then there is some dynamics. Now, if all the time derivatives are 0, then you have what is called a steady state process behavior, where there are no dynamics involved, and those types of equations will be algebraic equations. So, if you take this simple liquid level system as an example, you can write simple set of equations here. The fundamental basis of this equation is basic mass balance, and we will derive this in more detail carefully in a later lecture. For now, in this introductory lecture, I just want to show you the form of these equations and how we are going to relate these variables through equations. So, if you write a simple mass balance on the tank liquid, then you will get this equation where dH by dt is 1 over a Fi minus F naught. Fi is the input variable, H is the state variable, output is F naught. Now, if you look at this equation, this one equation, then I have 3 variables in this equation. I have H, Fi and F naught. Now, we generally know that if I have to solve for 3 variables, I need 3 equations, whereas here it looks like I have only one equation. And if you think about this little more carefully, you will notice that since we are writing the equation for the tank, and remember I drew a battery limit something like this, that means that the system equations themselves cannot define Fi. So, Fi has to come from outside. So, what you need to realize is that this Fi comes from outside. So, we do not have to count this as a variable for which we need to write a model equation. So, that leaves us with H and F naught, 2 variables, but I have only one equation. You can write the other equation for relating F naught and H in this form. We will again describe this in greater detail later. So, now I have one equation here, second equation here in 3 variables H, Fi and F naught. Fi is external to the system. So, I can solve this system of equations only if I know the value for Fi, and once I have a value for Fi, since I have 2 equations, I can solve for H and F naught. In fact, what you can do is you can substitute this F naught here, and then you will have a equation which has this following form: dH by dt is 1 over a Fi minus 1 over a C root H, and you notice that this equation is a differential equation in H, and Fi is what is called the input variable or a forcing function for this equation. Now that we have written the equation, then the next question is how are we going to use this equation in modeling this process. So, this equation or these equations are supposed to tell us how the output will change when I make changes to my input. So, in this case, if you notice that this is the input and this is the output. So, physically what we are asking is the following: if I change this input, so let us say this is a constant flow, and if I suddenly step up this constant flow, how do you think the outlet flow will change? Or if I suddenly ramp up this inlet flow, how will the outlet flow change? Or if I modulate this in a sinusoidal fashion, how will it change, and so on. So, if you look at the left side of this slide, we have shown various standard input forms, and the idea here is if you take the step input for example. So, what we are saying is prior to time 0. So, we arbitrarily say time 0 whenever we start that experiment, that is time 0. So, it does not matter when we start. So, if you started at the 3rd minute, that is time 0, if you started at 4th minute, that is time 0, and so on. So, if you think about this, so I have an input which is constant till here, it is at 0 when t is less than 0, and right at time t equals 0, I increase this input to value a. So, I step up the value of the input. So, physically that basically means that this f, let us say it was at some flow rate 5 units, I suddenly step it up to 10 units, or if it is at 7 units, I suddenly step it up to 10 units. Okay. So, you might wonder, I say 5, 7 and so on here, but here I have 0. So, basically what we do is whatever value I am at, I make that 0. So, for example, if I am at 5 and then I step it up to 7, that is equivalent to saying I am at 0 and I am stepping up by 2, right. So, whatever value of u, I subtract the steady state from that, then the first value is always 0. So, we will discuss this in more detail in terms of how we remove the steady state from these inputs and so on later, but the basic idea is what we are interested in is in the change, and we can always make the original value 0 by subtracting the steady state value. So, just as the name suggests, step is stepping up the input. Now, ramp is this form is 0 for t less than 0 and u is a t, t greater than or equal to 0. So, basically I have something like this straight and then it ramps up from here, and the slope is given by a. So, this is a ramp input, this is another standard input. The third type of input that we show here is what is called a sinusoidal input. Here we say okay, this u is 0 at all times and suddenly I start moving it in a sinusoidal fashion, where there is a frequency related term here omega or w, and this is a very important input. So, we will later see something called frequency response analysis, and you will see this is a very important input in terms of this frequency response analysis. If you had let us say 2 steps, so if you have initially like this, at t equal to 0 I bump this up and then hold it for some time, and after a while I bump it down, then this is called a rectangular input, which is shown as 0 t less than 0, it is a between t and tw, and after tw it becomes 0 again. So, this is called a rectangular pulse. You could also have an input which is very short acting. Okay. So, for example, in this case I have 0 up to here and then suddenly I give a and then immediately come back to 0. So, it is not really realistic to have a value for only time t equal to 0, because you cannot have. So, this looks like at time t equal to 0 I have 0 value a back again to 0. So, this is an idealization of something that is sharply changing. So, if I have here and something like this. So, this is an impulse input. Mathematically you could say something like this, it is at a when t is 0 and every other time it is 0. So, this you might think of as a mathematical idealization of this. So, you can get closer and closer to mathematics by doing this sharper and sharper and so on. So, the reason why we describe all these different types of inputs is that these are types of inputs we are going to see when we discuss the controller design and frequency response analysis and so on. Now, I just do not want you to lose the connection between the physics or the engineering system and the mathematics. So, if you want to kind of map this, all we are saying is, if I suddenly step up the input flow, that is step input, if I am slowly ramping up the input flow, that is this, supposing this flow I am increasing, decreasing, increasing, decreasing in a periodic sinusoidal fashion, that is this input. Rectangular input I suddenly increase, hold it for that value for a while and suddenly decrease it back to the original value, and impulses I suddenly open and have a lot of flow going and quickly close. So, that is impulse. So, what has happened now is the following. This is the physical process, this is a block diagram conceptualization, this is the math. Okay. So, this tank now the physical process has become a block. Now, this input flow is Fi, which is physically the input flow coming in, and you could say the liquid level or F naught, both are equivalent here, is the output of this process. Liquid level and F naught are related to each other. So, how this input could vary, we have shown through these multiple possibilities, and how do I convert this input physically? When I change something, clearly the flow is going to change. So, for example, if I step this flow up, because initially if this liquid is at steady state, that means Fi and Fo are the same, otherwise the liquid will not be steady. So, at a steady state Fi and Fo are the same. When I step up this Fi, that means the input flow rate has increased, whereas I have not done anything to F naught. So, the output flow rate is still at F naught. Then what will happen is, because the input flow rate has increased without the output flow rate changing, the height of the tank level will keep increasing. The minute this height increases, the output flow rate will also start increasing. So, after a while you will get to a steady state. So, that is what is physically going to happen. So, what we are trying to do is, we are trying to mathematically capture that physical behavior by saying, if I give you this, what will happen to this F naught, and the way we capture this tank has now become your set of equations. So, this block is the is representing the set of equations that basically tell you how physically, if I make these changes here, what I will observe and measure, I want to mimic using this equation. So, this is an important concept that I would like you guys to understand. The block is always some mathematical representation of what is physically happening. So, after a while when we are doing this course, we will start talking about only the math, we will have this input and this output comes out and so on, but I do not want you guys to lose this physical connection. So, whenever we are talking about input, it is a physical input, and whenever we are talking about output, it is a physical output. And in fact, what we are saying is once we model this, we do not have to actually go to a tank and do these experiments. We can run this model and then tell you what will happen. So, this might be the input. So, supposing I asked you something like this, if I keep changing Fi like this, what will F naught be? I do not have to go and do this experiment here in the tank to be able to get that. I can basically get that out of my simulation. So, what we have done in this slide is, for example, we have actually taken some values. Okay. So, we will say okay, initially let us say the height is about 9 feet, sampling time of 1 minute, and remember if you go back couple of slides, I have this constant c here, which I have as 1.5 here. A, the area is 0.5 feet square, and let us assume I am originally at steady state value of 4.5 cubic feet per minute. So, since I talk about steady state, at that point F naught will also be at 4.5 cubic per minute. Now, when we give an input, so the first input that we had in the previous slide was a step input. Let us say I step up my input flow from a particular value to a new value immediately. Now, I want to know what will happen to the height and subsequently to F naught. So, in this case, if you do the simulation and you can calculate the height of the tank using this, and once you get to a new steady state value of the height of the tank, you can always get your F naught as c times root of that the final value, or at any time you want to understand the dynamics of F naught and not height, it is simply F naught is c times root of h at any time, right. So, any time you want to know what the outlet flow rate is, it is going to be c times root of h, and that h is going to change according to this equation. So, h and F naught in that sense are equivalent as far as we are concerned for the explanation of this slide. So, if I step Fi to a new value, then the equations when we solve this will show that the height will change in this fashion. This you can actually observe if you actually do this experiment, because once you start increasing the inlet flow rate, that is you step up the inlet flow rate to a new value. As I mentioned before, because the outlet flow rate is still going to be at the same value initially, because of the flow mismatch there is more coming in, less going out. So, height will start increasing. Initially the height will start increasing rapidly, but the minute height starts increasing, the flow at the outlet will also start increasing because it is related as c root h. And since the flow starts increasing, the mismatch between the inlet flow and the outlet flow is going to be reducing, and because of that the rate at which the height increases will keep reducing. So, the rate at which the height increases will keep reducing till the rate becomes 0. So, the rate at which the height increases keeps decreasing till it becomes 0. At this point there is no change in height. So, this is a new steady state, and correspondingly you will have a new outlet flow rate at steady state. Now, as I said before, supposing you were to ask this question and say, look, I want to change my inlet flow rate like this. So, basically physically what we are saying is I want to increase it, wait for some time, decrease it back to its original value, wait for some time, increase it back to this value, and then wait for a much shorter time, bring it back, and so on. Supposing I have input function like this, and then I ask the question, how will the height change? One thing is you can do the experiment, the other thing is actually you can use the model that has already been built and then say this is how this is going to look. So, this is the output of the model for the height, and actually you could do the experiment and verify this is true or not. And these plots have been generated using this equation. So, really physically if you think of it as a tank here where the input changes and the height changes, the tank is being represented by these equations. So, the model then becomes a surrogate for the physical process, so that we can really work with this model instead of the physical process in designing our controllers, analyzing our controllers, testing our controllers, assessing our controllers and so on. So, that is the key idea of building a model. So, this is a very simple process example for us to describe how model works. Now, this will get lot more complicated, and also how do you go from here to here by solving the model is an important question that we need to answer. These are questions that we will answer as we go through this course. So, in this lecture I have given you an introduction to modeling and how models are used in control. In the next lecture I will talk about different control structures that we will use to look at controlling processes efficiently. And once that is done, then I would have given you a good introduction of how do you think about control systems, what are the important notions in control, how do you break a MIMO control problem into multiple CISO problems, and in each CISO problem we need a model. What does a model mean? What is a model doing, which is what this lecture was all about. And then once you get a model, how do you use it with control structures so that we can actually do control. So, with that I would have finished introducing you to the main ideas that we will see, and then after that we will actually talk about how you get these model equations in a systematic fashion, and how do you convert these inputs to outputs through these models in a systematic fashion, and how do you actually design controllers so that they can use these models and so on. So, with this I will end this lecture, and I look forward to seeing you in the next lecture. Thank you.